Chapter 11, Concept Preview. Okay, let's pick on one here. If f equals a cosine of theta, then what's df d theta? Yeah, but well, isn't it negative sine theta? Yeah. Okay. How about, we're going to use these a lot. That's why it says know them. I mean, you don't have to memorize it. You just have to find it every time. But okay, the integral would be what evaluated from 0 to pi? The derivative of cosine theta is negative sine theta. So we need a negative sign in there, right? Because when you take the derivative, it's these antiderivative ideas, right? Take the derivative of what's in the parentheses, you better get what's in the integral. Okay, we have to evaluate that from pi to 0. What's the cosine of pi? Let's see, we should have a little review here. Probably what should have been first is our, what do they call this? The what circle? Unit circle. Okay. The radius of the unit circle is it's 1, isn't it? Okay, it's 1. Now, the on the unit circle, you can draw all these, right, angles, right? And the radius is 1 all the time. Okay, the angle you go through is that little theta. Is it degrees? It's radians. You're supposed to use the word radians, right? Okay, so you go all the way around once. There it is, 4a. How many radians did you go through? 2 pi. There's 2 pi radians in 360 degrees. Okay, so let's back up a little bit. So you draw a little triangle here. I don't know, right there. Right. If I could blow that up bigger, that's my theta. Right? That's my theta. The length of the, see the triangle I'm trying to draw here? Okay. The length of the x side of that triangle is what? What do we refer to that as? The cosine of the theta. The length of the y side is the sine of the theta. Okay. So if I can go way out to cosine of, okay, now let's finish some of this stuff to make it easier. This is what we were after. That was all little, draw another unit circle. Okay. So they call this, right, that radius is 1, but it's also if you call it the x distance, I mean that's, oh, how do I say it? I'm trying to get at, this is 0 or 2 pi, right? You go through this whole distance, that distance is pi, right? This one's pi over 2. Remember seeing these distances, 3 pi over 2, right? Okay. So, and the reason why this could be 0 or 2 pi is, well, 0 would be you haven't gone around at all, right? 2 pi is you've gone around exactly once. you could write 4 pi. That would mean you've gone around 2 times. So it just keeps going, 0, 2 pi, 4 pi. So that's what you can keep calling this right here, the angles. This is the theta that we're talking about. Theta is these guys. So we're used to using degrees all the time. Life is a lot easier for cyclic measurements to be talking about radians. And you're going to see that a lot. So instead of saying the cosine of 69 degrees, you're going to say the cosine of, I don't know, some number pi over 6 or something. Right? You're going to see that a lot. And when you do that on your calculator, that's why we're messing around with this. Okay. Well, let's finish this integral here. And then we'll get into the calculator idea. We're jumping way ahead here. The cosine of pi is what? That's going to be the length of that x-axis. It's going to be -1. Do you see it? Because it's right here. What's pi? Pi is going to be this one right here. And we'll draw your little, the length of the x-axis. Well, that's -1. So cosine of pi is -1. And if you're never sure, just do it on your calculator, right? But -1 minus, so notice I pulled my minus sign out of the parentheses there. So the cosine of pi minus the cosine of 0. So the cosine of 0 is 1, right? So -1 and -1 is -2 times the negative sign, I get 2. Okay. And then the other dude, solve this guy. That's going to be what evaluated from 0 to 2 pi? What do you call that funky symbol? It's not a theta. A phi or phi. Phi, phi, pho, phom. I think I always called it phi. P-H-I. I always call that a phi. I don't know. Anyway, okay, phi. So it would be inside this integral then. Oh, sorry, it would be inside the parentheses, the antiderivative. Yeah, just the phi. There's the phi dude. Because the derivative of what would give you 1? Well, it has to be just the phi. Right? Okay. I have to evaluate that from 0 to 2 pi. I'm just going to get 2 pi. Well, if you don't skip anything, 2 pi minus 0. Well, 2 pi. Okay. Let's get 2 pi for that one. You'll be seeing those a lot. That's why they're in there. The how many radians are in 360 degrees? Juan told us 2 pi. Okay. On your calculator, what's the cosine of... The reason why we're doing this is because I want everyone's calculator to be in degrees. The cosine of 69 degrees is... what? What'd you get? 0.35? Okay. Folks are getting like 0.35. All right. Convert 90 degrees to radians. Well, if you knew the unit circle, you could say just pi over 2. But what if you didn't know the unit circle? You could just take it times, here's a conversion factor right here, right? There's 2 pi radians in 360 degrees. Because this will always work. And then, all right, you get 2 pi over 4, which is pi over 2. Same thing. How about 180 degrees in radians? That's pi. 0 degrees in radians. Yeah, it could be 0, or it could be 2 pi, or 4 pi, or 6 pi. Yep. I guess you can. Now, okay. Because all of these would really be, you can keep on going for all of these. Like this pi over 2, how can you get back to pi over 2 again? Just add what to it? One complete revolution. Add 2 pi to it. So pi over 2 plus 2 pi. Right, do your common denominator thing. So these answers keep going on and on and on. Okay. 5 pi over 2. Just keeps going. It could be pi. It could be 3 pi. It could be 5 pi. Right? It's an odd number pi. Just keeps going. This one could be 5 pi over 2. Just keeps going. Just keep adding 2 pi to it. Find a value for each. Cosine of pi. -1. If you're visualizing in a circle, you'd write a -1. Right? Cosine of 0 should be 1. Cosine of 2 pi? Yeah, it'd be 1 again. How about the sine of pi? That's 0. Because now we're looking at the y-axis. Sorry, yeah, the y-axis, the length of the y side. Sine of 0? Sine of 0, we are right here. The height of the y side is 0, right? Make sense? You see that? Sine of 13 pi plus 2 over 8. Oh, that's what calculators are for, I figure. Right? Now, to get the right answer, though, make sure you switch to radians. What did you get? 4? Really? Oh, I guess. I just made it up. -0.8 radians. 13 pi plus 2 over 8. Anybody else get that? -0.8 is what folks are getting. Are you in radians? So take 13 times pi, add 2 to it, whole thing, divide by 8. You guys have to use parentheses on yours. Yeah. And you get -0.8. Okay, so a lot of folks are getting that. Try the same thing for pi plus 2 over 8. 3.14 plus 2, you get about 5.14 divided by 8 in radians. What'd you get, Sandy? 0.59? Okay. Kathleen, did you get it? 0.59. Okay. Anna, what is the little I? Complex numbers have A plus IB. What's little I? Imaginary number, which is technically what? Close. Something that you put this in your calculator, you get error. Something to do with -1. Square root of -1. That's right. That's the square root of it. What's the A and the B? They're just what? Yeah, there's numbers. Right, there's numbers. Okay. Kinetic energy of an object of mass m moving at a speed v can be found through the equation Ke equals, Kathleen, what? Half mv squared. The same object would have a linear momentum p that can be found through the equation 1. I already picked on 1, that's okay. Little p equals anybody helpful? mv. Mass times velocity there. Use these two equations to derive the below relationship by starting with the kinetic energy equation. So start with kinetic energy. Drive. What could you do first? What would you do first? MV is a P. Oh, that's good. That's a good start. That's where I would start too. 1/2. You have the MV times V. We're getting close. Then what? What could you do next? You got to get rid of that V.
Can't you divide M to equals V to the other side?
Well, you can divide by M, but you also have to have it up on top then. It doesn't hurt anything. Right?
No, I mean,
No, this is good.
oh,
There it is. The MV is the P. Then the P times the P is the P squared. It works out. Okay. And 9, want to make sure you keep stuff straight because you're going to take whatever answer you get, right? Look at number 10. You're going to take the derivative of it again. So let's try to make our stuff look neat here. Take the derivative, the first derivative of kx. You just get what? Okay, so I guess you could say f prime. Remember doing that kind of notation? The prime meant the first derivative. Okay. F prime here. Adriana, what would f prime there be? Negative. Oh, you're okay. I like doing it the way you're doing it first. Negative sign ax, and then times a. All right? You're right. They pull the a out front all the time, but I like it doing this way because it's so much easier to see what she did. Take the derivative of what's on the outside first, chain rule. Take the derivative of the cosine, get the negative sign, whatever's in the middle, whatever is in the cosine, just write it there. Then take the derivative of what's on the inside. Okay. Let's see if we can get an answer for this one. 2 cosine squared kx. Identify what's the outermost function and work your way in. I see three functions in there. Do you see them? The square, and then the cosine, and then the kx. There's 3 of them. Okay, Alice, what'd you get? Four. Keep going, you're good. Kx. Negative Because now you got to take the derivative of the cosine. You just get sine, negative sign. Negative sign of what? Kx. Ah, I forgot my x. Slow it down. Slow down. Forgot my x. Okay. Then k. All right. So you have the square to worry about, and then the cosine, and then the kx. How about f equals 2e to the negative kx? Kathleen, how do you take the derivative of an exponential like that? That's inverse. It's inverse. It's the same thing again. So you take the derivative of 2e to the negative kx, you get 2e to the negative kx. Now that e is the outside function, you still have to worry about the negative kx. So then you have to take it times negative k. Because what's the derivative of negative kx? It's just negative k. Okay. So this can be a u-do. Taking the second derivative. Oh, except you probably should have a game plan for this one. 'Cause that's the only ugly one that I see. How many functions of x are in there? I see 2. So divvy them up so that you have your 2. Like, you could clean it up, but I say just call this one your first one, call that one your second one. Right, and then what's the rule for this? Take the derivative of the first times the second plus derivative of the second times the first. So it's not so bad. Okay. Differential equations, who knew? All right, this is a whole new course. So I'm not going to teach you or introduce you to all types of differential equations, just the ones that you're going to see. But if you can take a derivative, you can do integrals, you can do this stuff. I mean, it's really the same. You just have to know how to take derivatives. Substitute the function y equals ae to the ikx plus be to the negative ikx into the below differential and simplify it to get an answer. Okay. So we have negative h bar squared, some new constant, we'll talk about that later, over 2m second derivative. And then you got to put in what the y is all. What's my y? My y is ae to the ikx plus be to the negative ikx. So what does that equal? Well, the negative, that stuff out front doesn't do anything, right? Just leave that out there. Now, how do I do my notation? What's the first thing I should be writing here? How do we do it? How do we take second derivative? First, you have to write what first? Otherwise, you're going to forget to take it. The d dx, right? You have to write d dx first. Otherwise, you're going to forget to take the second derivative, right? So you have to write d dx first, and then you write your result of your first derivative inside here. A and B, they didn't say, but A and B's are just numbers. Okay. So what's the derivative with respect to x of ae to the ikx? It would be what? Yeah. A e to the ikx times the ik. Let's just bring the ik out with the a. It'll look easier to take the next one. Right? So let's just bring the ik out front. Otherwise, I have to have all these parentheses and stuff. Take the derivative of the second component would be what? Yeah, minus bik e to the ikx. Oh, it's like bike, doesn't it? Yeah. All right. Now we take our. Now we don't write d dx again, otherwise we'll never end, right? So leave that part out. Take the derivative of this first part, what you get? You'd have this a times, yeah, that ik has to be squared. Yeah, you're going to have that a, and then really that ik thing twice. You can write I squared, k squared, or just this. It really doesn't matter, right? And then e to the ikx. Then what? Same thing, but what it's gonna, I see a plus, don't you? Because then you pull that minus out, it's gonna make it a plus. Then it's the same thing. Okay, now we need to simplify it though, because we know what I is, square root of a -1. So what's the ik squared thing then? It'll be k squared, but times a negative k squared, because I is the square root of -1. So we'll have a negative a k squared. And this one will be, yeah, minus b k squared. There it is. Okay. Okay. Okay with that? Using integral tables and trig relations in solving complicated integrals. Okay, so if we ever see an integral of this form, we know what the answer is. Just use the formula. If you see this inside an integral, it's pretty hard to do. Substitute it with this. It'll be a lot easier to do the integral. Okay, let's do the first one. This guy is going to equal what? Which one would you use? Use the second one, yeah. So we got to substitute that stuff in. So you still have the 0 to pi part, but we need to substitute that whole mess in. 1/2 1 minus the cosine. Now what is my a going to be? Look at this guy. Sine square a theta. He is supposed to be matching with this. A is 1. A is 1. So it's just going to be 1 minus the cosine of 2 theta then. D theta. I think life would be easier to break. I think it'd be easier to see if we broke it up into, for me anyway, two. How many integrals? Two. Because remember, an integral is just the area under the curve. So if you add area plus area is area. So you can break up integrals. It's fine. So I think it's easier to see for some reason. It just looks easier for me. Let's see, 0 to pi. Okay. What's going to be in there? The derivative of what is going to give you a half? And my little variable is going to be the theta. Derivative of 2 would just be 0. Theta, yeah, half theta, because then the theta would disappear. Yeah, theta over 2 or a half theta. All right, that'd give me a half. Okay, minus the derivative of what gives me cosine 2 theta. Theta squared would just be 2 theta. Let's just write something. She said, isn't it like half sine 2 theta or something? Okay, let's take the derivative of it and see if it works, and then we can modify it. Oh, I forgot. All right. Take the derivative of half sine 2 theta. Derivative of sine is cosine. All right, then you got to take the... Doesn't this work? I think she guessed it right. Because you take the derivative of the sine, you get cosine 2 theta. Then you got to take it times what's on the inside. It should be a 2. But that's going to cancel with this guy. Oh, shoot, we forgot to multiply him through, didn't we? We should have... I'll just pull a stupid 1/2 out. Let's just keep pulling. Yeah, I'll just put it in there. Fine. Then we'll have 2 halves here, won't we? That's fine. Forgot to... Would have been easier to pull that 1/2 out of the whole stupid integral. Yeah. Speak up! Life's a lot easier then. All right. Well, that's okay. We're surviving. So all I did is just, you guys showed me I forgot to multiply through the halves. We put it back in front of the integral. So if it's in front of the integral, it doesn't matter, right? Life is still the same. Okay. Now we have to put in our stuff. We evaluate 1/2 theta from pi to 0. That's going to be pi over 2 minus 0. Okay, minus 1/2 times, okay. The sine of 2 pi is 0 on that unit circle. That's 0. Okay. Minus the sine of 0. 0 again. Oh, that guy wasn't so bad. Okay, so we're just left with pi over 2. Okay, let's try the next one. This guy, he equals, okay. Well, we're going to have to use this one for sure, right? So We need n factorial over a to the n plus 1. So what's my little n going to be? 3. So I'll write 3 factorial all over, what's my little a? Yeah, he's negative 2, isn't he? Or is he negative 2 or positive 2? He's just 2. Yeah, that little a has to be 2. Raised to the n plus 1, that's to the 4th. Okay, how do you do factorials? Yeah, 3 times 2 times 1, which is 6, divided by 2 raised to the 4th, 2 times 2, 4, 8. Is that 16? Is that 16? I can never do anything in my head. It's so sad. Okay, so that's 3 over 8. Right? So using these little tables, I think, is so much easier than doing things the way what we were doing. Here's another one. Integral 0 to infinity. No, that's the answer. Because according to the integral, if the integral is of that form, 0 to infinity, bam, you just write your answer. You're done. There's no evaluating from certain limits. So it's kind of nice. Okay, this thing. E equals. Okay. What's my n going to be in this case? 4. So I need 4 factorial. All over little a. He's going to be x over 8. A is going to be, what'd you say? 1/8. Because it has to be whatever's in front of the x. And it's just 1/8. So 1/8 raised to the n plus 1. So we said n was 4. Raised to the 5th. Whatever 1/8 is to the 5th. Well, if 3 factorial was, what the hell, 6, 24. I don't know. Things are just easier on the calculator. Does it matter if your calculator's in radians doing this stuff? Mm-mm. Nah, it doesn't matter. What did you get as an answer? 3.05 to 10 negative 5? Really? This doesn't sound right. It should be a big number. Oh, that's just the bottom part. Okay. Maybe a calculator, you do it all. And what's the top? What's 4 factorial? 24? Okay, yeah, that is going to be a big number, as I thought. What did you get? 786,000? Something like that? Boom. Okay. That could have been a you-do. That's okay. Triple integrals. Okay. Again, you can do one integral. If you can do a derivative, you can do an integral. If you can do one integral, you can do triple integrals. Why not? Right? It's just one thing applied to another. There's just a few tricks that you got to realize, and that's what I'm showing you. Okay, and this is the type of integral you're going to see anyway. Okay. Some notation first. Notice they're getting lazy. Instead of writing dx, dy, dz, they just write d. What's that symbol called? Rho is that. they call it tau. I think it's T-A-O. D tau. D tau is dx, dy, dz. Okay. So if we wanted to substitute that function in, all right, 1, 2, 3 integrals, 18x y cubed z plus 3 d tau. Okay. And we should put our limits in. X is supposed to go from 2 to 3, and y and z. So you recognize which integral is the x, which one's the y, which one's the z? It's dx, dy, dz. So I think the first one's x. Yeah. So 2 to 3. Oh, they're all 2 to 3. I shouldn't have done that. That gets confusing. Okay. Well, so all we're going to do is we're going to move all the x stuff into the x integral, and then take that times all the stuff that we can put in with the y, like his integral. I guess you could draw big parentheses here if it helps you. All right. Then all the stuff with the z, put him together. Find him. You'll have your answer. So they're all going from 2 to 3. Okay. Oh, heck, we could pull the 18 all the way where? Out the front. Let's do that for once instead of. Okay. So what's all my x stuff? It's pretty much just x. So that's all that fits in here. How about the y stuff? Y cubed. And the z stuff? Z plus 3. That's it. So what do you get? 18 times what evaluated from 2 to 3? X squared would be, the derivative of x squared is 2x. X squared over 2. Okay. What evaluated from 2 to 3? Yeah, y to the 4th over 4. Ah. And then what evaluated from 2 to 3? Z squared over 2 plus 3z. Yeah, I need more space. Okay. So we can make the rest of that a u-do. All right, because you have to put in the 3 for the x, right? So it would be 9 over 2 minus 4 over 2. And do that for all those. Okay. And then, a repeat, so we can make that another u-do. All right. Okay. Now to do that, we're going to have to use our integral property there, but okay. Again, you pull it into its 3 integrals, just all the x stuff, all the y stuff, and all the z stuff. Okay. Notice there isn't any y in here, so all you're going to do is just have the integral dy. Okay. Electromagnetic spectrum review. Well, this would be a good thing to wrap up on. What is the approximate wavelength of red light? Who did the UV viz yesterday? You do UV viz? Who did UV viz? Okay. Do you remember what the little x-axis was? What those numbers were? Yeah, wavelength. Okay, 400 to 700. What was the unit? Nanometers. Nanometers. Okay. So now is red kind of on the long wavelength end or the short wavelength end? Because she did a whole scale. Now let's back up a little bit. Emily said they're doing these food dyes, so they're doing the full spectrum, all colors. She said 400 to like around 700. So where does red fall? Is red on the short wavelength end or the long wavelength end? Red is on the long wavelength end. Red's on the long wavelength end. So red is going to be around 700. Red's on the long wavelength. It's around 700. It's a shade thing, right? I mean, 690, 680. Do you have deeper red? All these different shades of red. So I'll just say 700 nanometers. How about the violet? What's the name of that dude? All the colors? Roy G. Biv. Violet's on the opposite end of the red, so violet must be 400 nanometers. What is the energy in joules contained in a single photon of each? We need an equation. E equals... Well, yeah, that does. That's true, but that's not going to help. E equals h nu. E equals h nu. That's called nu. That's how I call it, nu. It's frequency. You also see it this way, but the book doesn't do it this way, hf. The book doesn't use f for frequency. The book uses this. This is speed, right? This kind of V-looking thing. If you make it big and fat and wide, that's your nu. That's your frequency. Okay, so this is big, fat, and wide. That's our frequency, or hf. But frequency is the speed of light all over its wavelength. Speed of light is which little symbol? C. Wavelength is what symbol? What do you call lambda? Lambda. Yeah. Okay, we're getting close. So here's our lambdas. But what's a nanometer? Nano is what prefix? 10 to the negative 9. 9. So 700 nanometers is 700 times 10 to the negative 9 meters. So that's what we'll put in for the wavelength. Little c is, what's that? 3 times 10 to the 8th meters per second. You can always just Google it if you forget. H is called Planck's constant. And you can just Google it. But I'm pretty sure, if my memory serves me right, I don't like doing this, 6.626 times 10 to the negative 34. I think that's it. You notice the energy units in there, joules. So you just put all that stuff in, you can get the energy of a single photon. The shorter the wavelength, the higher or lower the energy. The higher, yeah, because notice you're dividing by a smaller and smaller number. So yeah, we'll get higher the energy. Okay, so we're about out of time. So there's some you-dos in there, and then we'll spend the next class period on on the rest of this. So if you can knock out some of this, because all this additional problems on down is going to be homework, whatever we don't get done next class period. So if you get, there's not a whole lot of you-dos here. So if you can get some of this stuff done tonight, I mean, before the next class period, then you're going to have less homework in the end. So, and plus you'll be, oh, how do you do number 20 or whatever, right? So I would try to knock out some of these, especially see if you have any questions on them. But we'll spend the next class period on it.